When two disparate AI models process entirely different data types, like raw text and image pixels, they frequently arrive at the exact same geometric structure. This phenomenon is known as the Platonic Representation Hypothesis. Empirical evidence for this cross-modal alignment is overwhelming. As models scale and improve at their specific tasks, their internal representations become increasingly similar. However, there is no consensus on what these models are actually aligning toward. Current literature lacks a formal learning theoretic framework to identify the ground truth at the center of this convergence. Without a mathematical model, we cannot control or precisely engineer this alignment process. To understand AI convergence, we must decompose these representations into a strict statistical equation. This framework proposes that any learned representation consists of exactly 3 measurable components. This is the master equation that formalizes the hypothesis. The first component is the signal, the true Platonic ground truth. The second group represents bias, covering distortions inherent to architecture and training. The final variable is noise, which arises from limited training data. By isolating signal, bias, and noise, we can begin to reverse engineer the geometry of alignment. If we want to find the signal, we have to look for what stays constant across different models. That constant is the inference data, X. The structure of this data is described by the linear representation hypothesis. In this view, the world consists of objects defined by a sparse set of specific attributes. An object like a bridge breaks down into relational attributes, such as its role in transit infrastructure or its status as a tourist attraction. The variable z of x encodes this relationship as a sparse binary feature vector. Researchers validated this by using sparse autoencoders to extract these linear object attribute features from dense, messy representations. The results showed that when models are compared using these extracted sparse features, cross-modal alignment is consistently higher than when using raw features. This suggests that models are naturally attempting to map these sparse relations. The z of x signal indicates that models are mathematically driven to discover the structural reality of the objects they observe. If the signal is universal, we have to ask why raw representations aren't identical immediately. That brings us back to the bias variables, the dictionary A, and the magnitude weights M. Every architecture introduces approximation errors based on its specific design. Similarly, training procedures introduce optimization errors based on the model's specific objective. If this bias is systemic, a mathematical debiasing procedure should increase alignment across different models. The researchers tested this by subtracting the population mean and normalizing the raw features. Post-transformation, the representations shift into a significantly tighter geometric alignment. This trend is consistent across diverse datasets and various similarity metrics. Architecture and weights act as distorting lenses. Once we mathematically correct for them, the shared signal becomes much clearer. The final variable is eta, the random representational noise. This noise is a product of finite sample training, where limited data leaves gaps in a model's approximation. This scatterplot shows the correlation between word frequency and cross-modal alignment. There is a strong, consistent positive correlation between how often a word appears in training and how well its representation aligns across models. Abundant data leads to aligned representations, while data scarcity creates noisy, misaligned results. This observation helps explain why increasing the scale of training data consistently improves representation similarity. As we train stronger models on larger datasets, the noise term is driven towards zero, pushing models towards convergence. Reassembling the equation provides a structured view of why disparate models align. Platonic convergence is a predictable outcome of models successfully recovering the underlying signal. The sparse signal is the common target, often masked by calculable architectural biases and sampling noise. This framework shifts our understanding of machine learning development. Alignment is no longer just a curious emergent property, it is a metric we can actively engineer. We have the tools to influence it: sparse autoencoders to isolate features, centering to remove bias, and data scaling to eliminate noise. By mathematically addressing these components, we move toward building models that converge on a shared, consistent representation of the world.